Professor R. Asokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series in applied electronics. We have been going through a set of lectures on defects of images, which forms part of the paper Basics Physics 2, intended for the applied electronics students, which comes under semester 4, and the first chapter is on optics and it contains the defects of images. We have been seeing the various defects which are caused by lenses and mirrors. So, the lecture number 9, the contents are as follows. I told you about a chromatic aberration, the expression for the so called longitudinal chromatic aberration. Then the condition for achromatism when 2 lenses are placed in contact, the so called achromatic combination. These are the things that we will be seeing in today's lecture, and this is the kind of defect I have repeatedly shown, that a building which is looking like this is the original shape, and because of chromatic aberration you have this kind of colored tinge appearing on the right side, and the pillars which are erect obviously will appear to be slightly bent and colored and so on. This is so called chromatic aberration. I am asking you to note the difference between this figure and this picture. When white light is incident or made to pass through the lens, this leads to chromatic aberration, by which what I mean is the light rays which are incident on the peripheral region, that is the edges, right, and the light rays which are passing through this region, the inner region that is closer to the optic axis, they will lead to the focal points of violet rays and red rays. They are getting focused at different points. Therefore, the focal length which is there for violet and FR, that is for red, they will be different. So, the violet rays and red rays are not getting focused at the same point. If they are not getting focused at the same point, then that is called chromatic aberration, that will be obviously produced. And so, the distance that separates FV and FR is called the longitudinal chromatic aberration. The same is true in the case of a concave mirror also, about which we have discussed in a greater detail earlier. And now, we will go to obtain the expression for the longitudinal chromatic aberration. What I mean by longitudinal chromatic aberration is the distance that separates FV and FR. What is FV? This is the focal length that is produced due to the violet will be here, red will be here. The difference between FV and FR, as I told you, the violet and red will not come into the same focal point, right. So, the difference between FV and FR is called the longitudinal chromatic aberration. So, what we now observe is the first expression is nothing but the focal length of a lens, it is called a lens maker's formula, which goes as 1 by f is equal to mu minus 1 into 1 by r 1 minus 1 by r 2, where f is the focal length of the lens and mu is the refractive index of the material of the lens, and r 1 and r 2 are what? What are r 1 and r 2? They are the radii of curvature of the two surfaces. You got a surface here and you got another surface. You see the convex lens here, right? It is a thick lens. It is a thick lens having a radius of curvature r 1 and r 2 for the two surfaces, that is your r 1 r 2 are here, and this can be written as 1 by r 1 minus 1 by r 2 will be equal to this one. There are simple mathematical things, and now I can write down instead of mu, I will be using mu suffix v. As I told you, instead of f I will have f v and f r. V stands for violet and r stands for red. The focal length of the violet light and the focal length produced by the red light will not be the same. Therefore, I write 1 by f v as equal to mu v minus 1, you got here 1 by r 1 minus 1 by r 2. A similar expression I will be writing for the red ray also, that we equal to 1 by f r will be mu r minus 1 into 1 by r 1 minus 1 by r 2. So, 1 by f r will be equal to mu v minus 1 by mu minus 1 into f. So, you have got an expression here for 1 by f v and you have got an expression here 1 by f r. So, you have got r here mu r minus 1 by mu minus 1 into f, and you have got mu v minus 1 by mu minus 1 into f. So, now we can obtain the expression for f v minus f r. So, using the above two expressions which are obtained for 1 by f v and 1 by f r, I can write 1 by f v minus 1 by f r as an expression of this kind, which comes out automatically. So, this will be f r minus f v by f v into f r, the left hand side. The right hand side will become mu v minus mu r, you got mu v and mu r here, by mu minus 1 into f. That is the relation that you get now. That when simplified will give you, you write f v into f r is equal to f square, where f is the mean focal length for the two colors. We can rewrite the same thing, whatever expression that we had, as f r minus f v by f square to be equal to mu v minus mu r by mu minus 1 into f. Okay? This is what you are getting now. Now, in other words, f r minus f v will become equal to mu v minus mu r by mu minus 1 into f. F is the focal length again, and therefore, your f r minus f v will be omega times f. What is omega? The entire thing that you have got here, mu v minus mu r by mu minus 1 is known as the dispersive power, right. Omega is called the dispersive power. Now, therefore, we arrive at the final expression. Final expression of what? The distance or the spread of the focal length, right. The white light has different colors, they are getting dispersed. As I will show you now, it was shown by Newton that when white light, when it is incident or when it is passing through a prism, the white light gets split up into different colors. Now, these things are very old things, you have studied in high school, and so the white light gets split up into different colors in the order of Vibgyor. So, you get all colors, violet to red, right, violet to red. And same way now the prism, you have got a prism here, this is a lens that you have got here. So, the light rays which are incident on this region and similarly incident nearer to the optic axis, they subtend different angles, and that is the reason why, as is shown here, the red and violet are getting dispersed through different angles, the angle of dispersion. The white light would have gone in this direction because of the material of the prism, because you have got a prism here in the path of the light beam, it undergoes a angle delta r, that is the angle by which it is made to undergo refraction and emerging out, that is the angle by which it has been, its direction has been changed, that is your delta r. Delta r is smaller compared to delta v. The violet is getting displaced to a larger angle compared to the red line. So, that is the reason why the different colors do not come to a focus at the same point. It is because of dispersion when white light is passed through a lens. Now, therefore, you write your f r minus f e is equal to omega times f. This is important relation. So, the longitudinal chromatic aberration will be dispersive power times the focal length. So, this omega will be mu v minus mu r divided by mu minus 1. It is known as the dispersive power of the material. The material prism or the material out of which the lens is made, whether it is flint glass or crown glass, will be able to produce a dispersion. The dispersion means what? The angular range between delta r, that is the delta r and delta violet, right. The angular range between the red light and the violet light. What is meant by the dispersion? That is the the deviation suffered by the red light and the deviation suffered by violet, they are different. So, that will be your delta v and delta r. So, your dispersive power depends upon the material of the prism. What is refractive index? Refractive index is the ratio between the sine of the angle of incidence to the sine of the angle of refraction, but the careful wording should be remembered for a for a pair of media and for a given color of light. So, color is important. So, the wavelength of the light is important. I have told you in the last lecture also, the refractive index is a function of lambda. So, your refractive index for violet and red, they will be different. That gives rise to what is called the dispersive power of the prism. Okay. That is the reason why you got this kind of thing. So, you got an expression which involves the dispersive power, right. You write your f v minus f r or f r minus f e will be dispersive power multiplied by the focal length. Okay. So, this expression gives the longitudinal, the magnitude of the longitudinal chromatic aberration. Okay. That should be clear. So, it is a product of the dispersive power of the material prism or the material of the lens that you are talking about here multiplied by the focal length. Okay. And thus, the axial chromatic aberration is produced along the axis, right, the longitudinal chromatic aberration for a thin lens for an object placed at infinity is equal to the product of the dispersive power of the material of the lens and the mean focal length, because f is the mean focal length, right. You are taking f v, we had f v minus f r, f v into f r equal to f square, f is the mean focal length, and we show that f r minus f e is the product of dispersive power multiplied by the mean focal length. Okay. That is what I am stating here once again. And also it is clear that from the above that a single lens cannot produce an image free from chromatic aberration. Now, what I told you prior to the break is that it is clear from the above that the expression that you have got here, a single lens cannot form an image free from chromatic aberration. What do you mean by the statement free from chromatic aberration? Your chromatic aberration is present, then f p minus f r or f r minus f e will have a particular value. If it is 0, that means violet and red, they are getting focused at the same point, right. Do you understand this point? If f r minus f e is equal to 0, that means the focal length of red is equal to the focal length of violet. That means both the violet rays and the red rays will come to a same focus. So, the chromatic aberration is completely eliminated. So, so long as you use a single lens, because you have got an expression of this kind which says that f r minus f e will be equal to omega times f. F is the mean focal length, it is not 0, it cannot be 0, it is the focal length of the lens, right. Then omega is the dispersive power of the material out of which the lens is made. Omega is again mu v minus mu r by mu minus 1. Mu is the average refractive index or the refractive index of the glass lens or the flint glass or crown glass, whatever be the thing, and mu b minus mu r and mu, all these things are will be positive, right, will be having different values. Therefore, omega will have a different value, f will have a different value. So, the right hand side will have a particular value. Only if the right hand side is made to be 0, your f4 minus f will be equal to 0, the chromatic aberration is said to be completely eliminated. So, a single lens which gives rise to this kind of f4 minus f e to be equal to omega f, right, gives rise to two focal points which are separated by this kind of f4 minus f e. So, that leads to the chromatic aberration, because the right hand side has got a particular value. So, this chromatic aberration cannot be eliminated by using a single lens. It is impossible to have achromatism, that means the opposite of chromatism. So, chromatic aberration will be present if you are using a single lens. Now, what is the next step? You try to eliminate chromatic aberration or try to reduce the chromatic aberration. I have been telling you all along in the lectures on defects of images, the various aberrations which are present in the lenses and mirrors, such as spherical aberration, chromatic aberration, astigmatism, then what? Coma, distortion, all these aberrations can at best can be minimized. They can never be eliminated, because of simple reason you have got light rays incident on the peripheral region, right, and similarly nearer to the optic axis it is called axial rays, and they are called the paraxial rays, right. The paraxial rays, that is the light rays which are incident on the peripheral region, and nearer to the optic axis the light rays which are incident, they are called the paraxial light rays, because they are parallel to the optic axis. Now, these light rays will undergo different kinds of refraction or reflection in the case of mirror. So, they will not come to a single focal point, right, they will never converge at a particular point. So, because of the divergence you have the spherical aberration, chromatic aberration, coma, all these defects are there, and Newton had a lot of problems in devising his first telescope. So, he avoided the lenses. He thought the lenses will lead to chromatic aberration. It is Newton who observed dispersion, right. The credit of showing dispersion of light, when white light is passing through a prism, you get all the colors. It is observed by Robert Hooke, but the credit went to Newton, because Hooke did not give a proper interpretation. I mean, he was not very sure of what he was observing, and he thought it may be due to the defect of the material and so on. So, Robert Hooke was not given the importance, even though he was the first to observe the phenomenon of dispersion, and the credit of observing dispersion went to Newton, and we all say that Newton observed dispersion. Okay. And so, a single image cannot completely eliminate chromatic aberration. You see, what is this lens? This is a convex lens. Okay. Now, if this gives rise to a chromatic aberration, what shall we do? We try to have a biconcave lens, right. You see a lens here is a biconcave, right. You have got a curved inwardly. Now, this is curved outward, right, curved outward, this is also curved outward. A plano-convex means one surface will be plane, the other will be curved. It is a plano-convex, or you can have plano-concave. The one surface will be plane again, the other will be bent inward, right. It is a plano-concave or a plano-convex. This is a biconvex, right. It is a convex lens. On the other hand, it is a convex lens. This is a biconcave, right. Now, let us see that historical, there is a very beautiful story. Now, people try to eliminate chromatic aberration. One man went and gave it to a person to study this, what is the kind of defect you are getting, and another man went to the same person, the company person, to see what kind of defect you are getting, and what he did is to combine these two, right. So, whatever defect that is produced here can be annulled. This is a convex lens, right. This is a biconcave. The defect that is produced by this can be annulled, because convex is it is leads to some kind of defect. The concave should do the opposite thing. So, you combine these two, right. The convex and concave biconcave can be combined to reduce or minimize the chromatic aberration, and if you do that, that is called a achromatic doublet. There are two lenses, one is made up of flint, the other is made up of crown. So, the material is different, the nature of the lens is also different, one is biconvex, the other is biconcave. So, you can combine two lenses, and again which are made up of two different materials, in what way you have to combine in such a way that the F4 minus Fv becomes equal to 0. Okay. So, let us now pass on to the condition for achromatic combination. Supposing you got two lenses, as I told you just now, you combine a convex lens with a biconcave lens and produce the achromatic combination, right. An achromat is made by placing in contact two lenses made up of two different materials having suitable focal lengths, such that the focal length of the combination is the same for both the extreme colors, for violet and red. So, the angular thing should be annulled. So, the defect caused by convex should be annulled by the concave lens. It means the focal length of the achromat is independent of refractive index. Let the lenses of the doublet have the mean focal lengths f1 f prime and the mean refractive indices of the materials, or mu and mu prime. I am talking about materials, that means one is made up of flint, the other is made up of crown, and I got the focal lengths are different, f and f prime, and you can write as in the earlier case, you can have an expression for 1 by Fv and similarly 1 by F4, and the resultant things of, or they go as follows, right. Mu v minus mu 1 here, mu r minus mu 1 in the numerator, other things are the same. Now, you can try to have 1 by Fv prime to be equal to mu v prime by mu prime, where mu prime is what, the for the second length of focal length f prime and refractive index mu prime, and you got an expression of this kind, and 1 by F4 prime will be equal to mu r prime by mu prime and multiplied by 1 by f prime. This kind of mathematics will lead you to have the ultimate expression. I will go through the mathematics anyway for the sake of completion. There are simple steps. 1 by Fv will be equal to this kind of relation you got connecting mu v and mu v prime, and 1 by F4 the focal length for red will be involving mu r and mu r prime. Okay, the refractive indices for the red of one material, the other one mu r prime is for the other material. As I told you, one is the crown glass, the other may be a flint glass, and the combination to be achromatic, the focal length Fv and F4 must be equal, or Fv will be equal to F4, that is what I told you now, or 1 by Fv will be equal to 1 by Fr. And so, whatever you got 1 by Fv and 1 by Fr should be made to be equal to one another. That means, you have to equate the right hand sides. So, when you equate the right hand sides, then you get mu v minus mu r by mu minus 1 into f plus mu v prime minus mu r prime by mu prime minus 1 into f prime is equal to 0. That is the condition for an achromatic doublet. So, that what is your mu v minus mu r by mu minus 1? Nothing but the dispersive power of the first lens. Okay. You are having two lenses now, omega is the dispersive power. How do you define the dispersive power? All of you know, in the case of a prism, the difference in the refractive indices mu v minus mu r by mu minus 1 is known as the dispersive power of the material of the prism. Similarly, here for the first lens, you have got mu v minus mu r by mu minus 1, that is the dispersive power of the first lens. For the second lens, you will be having again omega prime, that is dispersive power of the second lens divided by f prime will be equal to 0. Okay. That should be equal to 0. So, the whatever that you got here, it is your omega prime that divided by f prime should be equal to 0. or in other words f prime should be equal to minus f into omega prime by omega. Okay. F prime, that is focal length of the second lens, should be minus of the focal length of the first lens. What do you mean by this statement, this expression? That means, if you got one is the focal length of the convex, right, other should be minus, means it is biconcave, right, biconcave. The convex lens got a focal length f prime, the biconcave should be having a focal length minus f. So, the two lenses which are made should be of different nature, in the sense one is convex, the other should be concave, and the doublet should be annulling the defect caused by a single lens. As I told you, a single lens will always lead to a defect image. So, you have now the two things should be annulling each other. Therefore, let me now show you a combination of flint glass with a crown glass, right, will lead to what is called a achromatic doublet. That means, chromatic aberration will be completely eliminated. Let me now summarize the lecture. The expression for the longitudinal aberration is found to be equal to the product of your omega and f. A convex lens of crown glass is made to be in contact with a concave lens of flint glass in order to make an achromatic doublet. Now, we have the question session. You have the question number 1, give the expression for the longitudinal chromatic aberration. Question number 2, express the condition for achromatism when two lenses are kept in contact. The last question is, what kind of lenses and materials are to be used to make an achromatic doublet. With this, we come to the end of the lecture number 9. We have completed the lectures on defects of images. Now, we will move on to the section on interference in this chapter on optics. Thank you.